For this coding example, we will work with Fashion MNIST dataset. Now, before we go to our dataset and the model building, just a recap of what a life cycle of a neural network model in Keras is. The first step, define the model, compile the model, fit the model, evaluate, and finally make prediction. So coming back to the Fashion MNIST dataset, the Fashion MNIST clothing classification problem is a new standard dataset used in computer vision and deep learning. Now, although this dataset is relatively simple, it can be used as a basis for learning and practicing how to develop, evaluate, and use deep convolutional neural network for image classification from scratch. The Fashion MNIST dataset is directly available in TensorFlow and Keras libraries, so we can import this dataset directly from these libraries without actually downloading it into our computers. So, as I mentioned, Fashion MNIST dataset is proposed as a more challenging replacement dataset for the MNIST dataset. So, I hope you are already familiar with MNIST dataset. So, MNIST dataset is a dataset for handwritten digit, right? Handwritten digit. So, Fashion MNIST dataset, on the other hand, consists of clothing images. So, as you can see, these are some of the images present in our Fashion MNIST dataset. And as you can see, it has 60,000 training examples. That means this dataset is compressed of 60,000 small square images of 28 cross 28 pixel, and it is a grayscale image. And this dataset also provides 10,000 test examples, and it has 10 different classes. So it has 10 different classes in order to represent 10 types of clothing, such as t-shirts, trousers, pullovers, dress, coat, ankle boots, etc. So these are the 10 different classes available in our Fashion MNIST dataset. So definitely, if you are trying to solve an image classification problem using an MNIST dataset, it means it is a multi-class classification problem. So let us get started and use this MNIST Fashion dataset as a starting point for developing and practicing a methodology for solving a very simple image classification using the specified architecture we have studied, which is the CNN, or convolutional neural network. So let us get started. To start with, let us build a baseline model. Now, this is a common way how we work with real life problems or very large data sets. So what we do is build a small baseline model, and once you have this baseline model ready, you will evaluate the performance of this baseline model. And then what we can do is we can add advanced features on this baseline model, evaluate those advanced model, and then compare its performance with the baseline model. So you have a clear picture of whether the modification that you are adding is actually improving the performance of your model above your performance of the baseline model. So for example, if you are building a CNN, what we can do is in the first convolution layer, say I had 32 filters, and then form a simple CNN model with that architecture. But advanced model is what you can do is you can now tweak the number of filters and probably change it to 64, and you can see whether this modification is actually improving the performance of your model or not. So it's a good way to get started to build a very small, a simple baseline model and then build on top of that baseline model. So let us get started and build a very simple baseline model for our fashion MNIST image classification problem. So the first step to start any programming is to import all the necessary libraries, right? Now once we are done with that, the first step in creating a baseline model is to actually load your data set. Now there are things that we already know about our fashion MNIST data set. That is, it is a 28 cross 28 pixel data set, and it is a grayscale images present in that data set. So again, one more thing is that it is always good to write your program as functions, as small chunks of functions, because the functions are very much handy and it is very much reusable. So first what we are doing is we are writing a function to load our MNIST data set. So as I have mentioned, since the MNIST data set is directly present in our Keras library, we could directly load it from the library, right? So I have my train and test. So the 60,000 training data set will get loaded into TrainX, and the 10,000 in our in our TestX, and similarly with its labels in the train Y and test Y. Now it is now important to reshape the data set to make sure that the Keras is able to read it and use it effectively. So the point of doing this is that the Keras takes the data set in the following manner, that is number of images, comma, image width, image height, and color dimension. That's how I have reshaped my data set according to the way Keras understand it. So trainx.shape will actually give you the number of images in your training set, which is 60,000 as we know, and then followed by image width. So image width is 28, image height is 28, and since it is a grayscale image, the channel is 1. So it is one of the first point that you have to do to reshape your data set so that it is in a way that the Keras library can understand it effectively. So I have reshaped my TrainX and TestX. Now once that is done, the second important thing that is to be done on this data set is to actually perform a one-hot encoding. Now, and this can be performed directly with the help of the utility function that is available, which is called as underscore categorical. So we already know about our data set that it has 10 different classes, and these classes are represented by unique integers, or they are categorical values. So when you have that, what you need is to convert these categorical into one hot encoding, so that the class element for each sample is transferred into an integer value of 10 elements. Or put in other words, if you have a class of label 0, it would be converted into say into 0 0 0 0 0 0 0 0 and 0, right? Or one more 0. So this is something which belongs to class 0, whereas if your label belongs to if your image belongs to label 1, then the one hot encoding will be this. If it belongs to label 2, then the one hot encoding will be like this. So it is important that we actually transfer our categorical values, which are the labels present in our data set. In the case of our MNIST data set, it's from 0 to 9, into a one hot encoding, and this is directly achieved by the utility function in Keras, which is called as to_categorical. Now once you have done that step of loading the data, and in the same function I have converted my labels into one hot encoding. So that makes my first function load data set. Now the second step that I need to take is to prepare my pixel data. So we know that, and for that I have written this function called as prep_pixels. So we know that the pixel values for our image data sets are unsigned integers from the range of 0 to 255, that is black and white. So 0 to 255. So here what we need to do is we need to normalize our pixel values of our grayscale image, or resize it into something between 0 to 1, and the best way to do is to divide it with 255. But of course the division can lead to floating point values. So in order for my code to deal with floating point values, I have already converted my train and test values into train and test x values into a floating point digit, and then I am dividing that into with 255 so as to normalize my pixel values within a range of 0 to 1. So these two functions, that is to load the data set and to prepare the pixel, actually comes in the pre-processing phase, right? We need to pre-process our data set so that it is suitable to train my model or build my model on that data set. So these two can be considered as a pre-processing stage, right? And depending upon your problem statement, depending upon the data set you are using, you will have to adjust between the pre-processing stage. Now once that is done, as we know from the life cycle of our life cycle of our Keras, the first stage is define the model, compile the model, fit the model, evaluate, and finally make prediction. So now let us go ahead and define our model. So here I have written the function to define my model, and as I have mentioned, I am building a baseline model, or I am building a very small model, a small architecture, right? So we are building a CNN, a basic CNN architecture. And as we know, the CNN architecture has got two aspects to it. One, which is the feature extraction, which is comprised of the convolution and pooling operation, and second one, which is the actual classification, right? So as we know, as you can see, I'm building a sequential model API. So my first convolution operation, there is only one convolution layer, and so that is, you have only one convolution layer, and in that I have a conv operation and a max pooling operation. And as you can see, for the conv operation, I have used a filter size of 3 × 3. I have used a number of filters to be 32. I have used my activation function to be ReLU. I have initialized my values, that is, my values that will come in my 3 × 3 filter with a He uniform initializer, and I specify my input shape to be, of course, 28, 28, 1. After that, I have my pooling operation. As you can see, I have used a max pooling with a window size of 2 × 2. Now, as I have mentioned, since in the last video on coding, that if I haven't provided the stride, it automatically takes the none value, and the default none value points to the size of your window size of your pooling. So that means we are using a stride of 2 here. So after that, I am flattening my resultant image, or the resultant object, or resultant tensor, and then of course passing it through a fully connected neural network which has 100 neurons, again the activation function ReLU and our kernel initializer. And soon after that, I have my output node, which of course should have 10 nodes because I have 10 different classes. And of course, since it is a multi-class classification problem, I have used a softmax. So as you can see, the model I have built is a very small model with just one convolution layer, with just one fully connected neural network, right? And after that, definitely the next step after defining the model is to compile the model, right? And for that, I have decided to use stochastic gradient descent, as you can see here. Stochastic gradient descent with learning rate of 0.01, momentum of 0.9, and since my loss function, since I'm dealing with a multi-class classification problem, as we already know, the one choice of loss function is categorical cross entropy, and to measure the performance, I have used the accuracy metrics because this is a classification problem. So in this particular function, define the model, I have not only defined my model, but I have also have my code for compiling the model. So the first two stages or steps in the life cycle of a Keras is dealt with in this particular function. Now once the model is defined, what we need to do next is to fit our model. That means I need to train my model on the training data set and test my model on the test data set. Now for this purpose, I'll be using a cross validation, a 5-fold cross validation, as you can see from here. So when we use a cross validation setup, we are further splitting our training set into train and validation set. But in this case, the validation set is written as the test set, test X and test Y. So this is not the actual test set from our MNIST data set, because we know MNIST already have 10,000 data samples in the test set, but this is not the MNIST test set from the MNIST data set, but it is just it's the validation data set or the holdout data set, right? So since I have like 60,000 training data set, and I'm dividing it into 5 folds to do my validation, cross-fold validation. That means every fold will have approximately 12,000 data point. So performance on this train and validation set over each run can also be plotted into a learning curve in order to understand how well my model is learning over each of the iterations. And then the performance of the model can then be taken as the mean performance of the k-fold along with the standard deviation, which could give us an estimate of the confidence interval. Now, in order to train our baseline model, as you can see, I have used a very modest training epochs, which is 10, but still it will take a lot of time to train this 10 epochs, batch size of 32. And see here, you can see the validation data is my test X and test Y. So this is not the test X and test Y, which is the testing data from the MNIST Fashion MNIST data set itself, but it is the same. It's the training data set which has now been divided into 5-fold. So the test set for each fold will be used to evaluate the model both during each epochs of the training run, so that we can later create a learning curve, and at the end we can take the estimate of the model performance. So the next life cycle of the model is also done, that is to fit the model and then to evaluate the model. Now, once that is done, an important thing which is not regarded as a life cycle, but it's a very important when you are working on a problem, is to present the result, right? So once the model has been evaluated, we need to present our result, and there are two key aspects or two key ways in which you can present this result. The first one is a diagnosis of the learning behavior of the model during the training, right? That is during the training on the five-fold during the 5-fold cross validation, and then the second one is the actual model performance. So this can be implemented. This has been implemented as two separate functions. So first you can see this function is used to plot your learning curve, wherein which the blue lines will be used to label your or indicate the model performance on training data set, and the orange color will be used on the to show the training on the holdout data set. So these learning curves or these plots are very valuable for getting an idea of whether a model is going to overfit or underfit, or if it is a good fit for your data set. Now, another method of performing presenting the result is, of course, to take the a classification accuracy score, which is nothing but the mean or average of your 5 folds. And also you could provide a standard deviation value so that you can get a confidence rate on this predicted accuracy. And once that is all done, it's just the matter of calling each of the functions. So as you can see, the first function that is being called is the load data set. The second function that is called is the prepare pixel. Third is the define model. Fourth is the evaluate model function. And then finally the last two call are for presenting the result, that is to make the learning curve and to show the average score. So let us go ahead and run this code and see the result. So once you run the code, you could see actually the accuracy for each of the fold, right? And finally here you could see the mean accuracy, which is approximately 96, and the standard deviation of 3.4. And you could also see at the top the line, the learning curve for each of the 5 folds, and also a box plot which was again used here. So you could see that for the average mean, I have also asked to plot a box plot in order to show the plot the accuracy for each of the 5 folds. So this is also given. So this looks to be a relatively good model. So this is our base model, a very small base model. In the next video, we will try to see if this base model can be improved by making some tweak on our model architecture. That is, what will happen if I add a padding layer? How will it influence my accuracy score? What happens if I increase the number of channels? How will it affect my accuracy score? Or if adding more convolution layer have an effect on my accuracy score, and so on. So once you have this base model ready and you have have an idea of a estimate of what the accuracy of this model is, it's always easy to build your architecture on top of this base model, and then evaluate those advanced architecture and see if they are actually increasing or decreasing the performance on your data set.